All right, we're looking at the last section of the topic 6 notes, talking about polygons, and we're talking about quadrilaterals. Now, the other day we talked about parallelograms. That was one of our subcategories of quadrilateral. Quadrilateral was the big overall category. Anything with four sides and four angles could be called a quadrilateral. And then we went and talked about some specifics that can make something into a parallelogram. Well, today we're going to talk about the other two of these subcategories, trapezoids and kites. All right, those are the two things we're going to be looking at today, and let's get rolling on that. All right, first off, the definition of a trapezoid is this. Okay, it says that it is a quadrilateral, so four sides, and it only has one pair of parallel sides. So, unlike a parallelogram, when on a parallelogram you had two pairs that were both parallel, the opposite sets of sides were parallel to each other, and there were two of those sets. On a trapezoid, like on this right here, you only have one set. So, on this picture, it'd be AB and CD are the two parallel sides. All right. So, you've always got one set of parallel sides like that, and the other two sides are not parallel. Those non-parallel sides are called the legs of the trapezoid, and the parallel sides are called the bases. Each trapezoid has two pairs of base angles. What that means is exactly what it sounds like. The base angles are where the leg meets the base. So C and D, those together would be one pair of base angles, and A and B would be the other pair of base angles. All right, so just like we talked about within quadrilaterals, trapezoids is one of those subcategories, and kind of like parallelograms had could be categorized even further as a rhombus or a rectangle or a square. An isosceles trapezoid is a subcategory within trapezoids, and that's a special kind of trapezoid where the legs are congruent. Okay, so that little symbol, the equal sign with inye, means congruent. So that is congruent legs. Um, so what that means on our picture right here is that this side and that side are the same length. We give them both one mark. Okay, what that does for us is it creates a situation where each pair of base angles are congruent. So that means when we look at this picture, this angle right here and this angle right here are congruent to each other. This angle on bottom and this angle on the bottom are congruent to each other. Okay, base angle pairs. Okay, both of the angles attached to one base are congruent if it's an isosceles trapezoid, and that's one of your subcategories. The other situation we get is this: the diagonals are congruent. So that's talking about, remember, your diagonals on a quadrilateral is when you connect corner to corner. When you're connecting opposite angles like that, the lines that connect the opposite angles are the diagonals. And on an isosceles trapezoid, those segments would be the same length. All right, moving on now to the mid segment of a trapezoid. Okay, that's talking about that's a word that we've heard before, right? Mid segment. When we talked about it with triangles, that was the line segment that cuts across the middle of a triangle and connects midpoint to midpoint on the sides of a triangle. Well, on a trapezoid, it's the same idea. It's a segment that connects midpoints of the legs. So if we picked out and found the midpoint in between A and D, that's somewhere probably about right there. In between B and C is somewhere probably about right there. And if we're drawing the mid segment, we're just connecting those 2 points together. All right, it is, that's kind of a rough sketch, but it gets the idea across. We're connecting midpoint to midpoint. Now, since we're connecting midpoint to midpoint, that means that this piece on top and this piece on bottom are the same. It means that these two pieces are also the same. Okay, remember, the midpoint is the point in the middle, so the pieces on each side of it should be the same length. Up next, we want to talk about the length of it. Okay, it says that its length is 1/2 the sum of the lengths of the bases. Okay, that is a fancy schmancy way of saying that this mid-segment length equals the average length of the bases. So in this case, base 1 and base 2, That's the length of AB. That'd be base 1. And this down here would be base 2. Oh man, that's some good handwriting I got on there. All right, base 1 and base 2. Okay, we're finding the average length of this top base and this bottom base. That's how long the mid segment is. All right, add them together, divide by 2. This next section right here is asking to figure out if each statement is sometimes true, always true, or never true. This first statement is a trapezoid is a parallelogram. Well, I want to draw your attention back to some of the properties of parallelograms further back in your notes packet on this page. No, not that one. It's on. No, it's not that one either. I know it's on here. So here we go. This page right here. Okay, the first thing that we talked about with parallelograms is that opposite sides are parallel. That's talking about this side and this side. We've got one set of parallel sides right there and one set of parallel sides right there. Okay, you've got four sides and it's split into two sides are parallel this way, two sides parallel that way, and that's how we get two pairs of parallel sides. Well, when we look at the definition of a trapezoid right here, we have only one pair of parallel sides. So it raises the question, how is it possible, or is it even possible, that a shape could be a parallelogram with two sets of parallel sides and also a trapezoid with only one set of parallel sides? And the answer is no, that's not possible at all. So the answer to this question, is it sometimes true, always true, never true? This one is never true at all. It's not possible to have one set of parallel sides and two sets of parallel sides. Okay, the next statement, the bases of a trapezoid are parallel. Now, we just got done saying that a trapezoid always has one set of parallel sides, right? We've got exactly one pair. That's what we wrote on this page right here. Only one pair of parallel sides. And we also wrote down the parallel sides are called the bases. This is something that is always true. Up next, the base angles of a trapezoid are congruent. When we talked about base angles, we said that every trapezoid has them. Okay, every trapezoid has pairs of base angles. But this right here, the isosceles trapezoid, where we're talking about base angles being congruent, well, that is something that only happens with an isosceles trapezoid. Okay, look at what happens. What if I drew a trapezoid that looked like this? All right, we've got our parallel sides right there like that, and then our legs right there. Now you can tell just looking at this shape that this angle on this side and the angle over here on this side are not the same size. Okay, those base angles are definitely not congruent. Okay, but since this right here, since this side and that side are parallel, that's a trapezoid. All right. So what we're saying is, if it's an isosceles trapezoid, this statement is true, but not every trapezoid fits. Not every trapezoid is isosceles. So this is sometimes true. This statement is sometimes true. This next one right here, the legs of a trapezoid are parallel. All right. Looking at this one, our definition says that there is one pair of parallel sides, and those are the bases. Okay, the legs are not parallel. If we had legs that were parallel, it wouldn't be a trapezoid, because then you'd have two sets. Okay, you can only have one set in a trapezoid. That's the definition of it. So that means this is a statement that is never true. All right, moving on now to our next one, talking about kites. This is on the very back page. All right, it says this is a quadrilateral with two pairs of consecutive congruent sides. Now, this is a little bit different than a parallelogram, okay? When we talked about parallelograms right here, we said that opposite sides are congruent. That was the definition. One of the things that makes a quadrilateral a parallelogram, something that makes it different from other quadrilaterals, is that opposite sides are congruent. Well, when we look at kites, a kite is set up so that you've got consecutive congruent sides. Okay, that means the sides next to each other are the same length rather than the sides that are opposite from each other. Okay, opposite sides are not congruent. When you look at a kite, the longer diagonal called the main diagonal, bisects the shorter diagonal. All right, so it's kind of hard to see on that picture. Let's see if I can zoom in a little bit. It's kind of hard to tell. Oh, come on now. Here we go. It's kind of hard to tell on some of these pictures. Oh my goodness gracious. All right, let's just come on back here. As I say, it's hard to tell on this picture, kind of, but this right here, oh, there we go. We've got hash marks. We've got 2 marks on this top piece and on this bottom piece. And that means it's bisected. All right. The other thing about kite is that the diagonals are perpendicular. So on your test review coming up, there's going to be a question that asks you if the diagonals are perpendicular, what kind of quadrilateral could it be? And so it could be a kite, or it could be a rhombus. That was one of the things we talked about with a rhombus, or it could be a square, because a square is a rhombus, right? Now, this last one right here, I think is kind of interesting, and it has to do with some of the stuff that we talked about a couple of units ago. Okay, if a quadrilateral is a kite, then one pair of opposite angles are congruent. Now, you can tell just looking at this picture on this kite, MATH. You can tell that angle M over here is smaller than angle T. So if we're talking about exactly one pair of opposite angles, it's going to end up being A and H. Okay, that's half your answer. Which pair of angles would have to be congruent? It's going to end up being A and H. But the question is why? And I want to draw your attention to what happens when you draw the diagonal across this. All right, when we draw that diagonal from M to T, that splits our quadrilateral into 2 triangles. Yeah, we've got 2 triangles right there. Now the question comes up, how do we know that this angle and that angle are the same? Well, back several units ago, we had a lot of pictures that looked like this, and we had to use a bunch of theorems like SAS or AAS. Remember all of our triangle congruence theorems? We had a bunch of pictures that looked like this. And whenever you had a line that cut through the middle of your shape, you had to recognize that that was a congruent side. Okay, there was never any markers on it, but you had to know that for the triangle on top and the triangle on bottom, that was a congruent side. And so what we have right here is a case of, well, let's go through it. We've got one side that's congruent right there. We've got one side that's congruent right here. And we've got that side that cuts through the middle that's congruent for both of them. This is a case of side, side, side congruence, y'all. So when we talk about this right here, the reason that A and H have to be congruent is because triangle MAT and triangle MHT are congruent, and angle A and angle H are corresponding parts of congruent triangles. So when it asks why are those congruent, you've got 2 answers. First is side, side, side congruence. All right. Side, side, side tells us that the triangle on top of this, the triangle on bottom of this picture are congruent to each other. Up next would be CPCTC. Congruent or corresponding parts of congruent triangles are congruent. Okay, that tells us that A and H are corresponding angles, so they have to be congruent as well. Go on now to this problem right here. It tells us that this shape is a kite. It tells us that the lines cutting through the middle right here are the diagonals. So first off, we ask the question, what kind of triangle is PQT? PQT right there. And the answer is this. It's a right triangle. So you ask yourself, how do we know that's a right triangle? There's no squares right here. How do we know that this is a right angle? And the answer is right here in the definition. Okay, a kite's diagonals are perpendicular. So that means PQT has to be a right triangle. You can draw the little square in that corner right there to make sure you know. Now, if we're dealing with right triangles and we're trying to, in this next question, find the perimeter of PQRS, then we need to know the length of this part right here, and we need to know the length of all of these sides on the outside. That's what we're looking for. We're looking for the length of everything on the sides right here. Now, finding the exact perimeter of PQRS, we're going to start by finding this one right here. Now, if you look at this, we've got two sides of a right triangle, and we're looking for the third one. Y'all, we can use our old friend, the Pythagorean theorem. A squared plus B squared equals C squared. Now, here's the thing about the Pythagorean theorem. When we talked about this a couple of weeks ago, we noticed that most of the time, you're not actually worried about what C squared is. Okay, it doesn't really matter what C squared is. If we're looking for the length of this side of the triangle, we need C. Okay, we have A and B, it's those two legs, but we need C to get the outside of this shape. And so what we do is we can just take the square root. We take the square root of C squared, and that gives us C by itself. But what that does on the left side of this equation is it makes it to where it's one big old square root. Square root of A squared plus B squared. Okay, you take the square root of everything on the whole left side of that equation. That's what we get right there. This is the arrangement that we're going to be using right here, okay? So here's what I'm thinking. If we can get the hypotenuse right here and the hypotenuse of this other triangle, the hypotenuse of this triangle that I'm outlining in orange, if we can get those two hypotenuses, we'll be well on our way to finding the perimeter of the outside of this shape, yeah? And so that's exactly what we do. For our first triangle right here, our A and B are 4 and 4. That's the two lengths of the legs. For our other triangle, we've got leg lengths of 4 and 8. So under our square roots, we've got 4 squared plus 4 squared. We've got 4 squared plus 8 squared, okay? This is our red triangle, and this other one is our orange triangle right there. All right, so we go down and we can simplify stuff as we go. Remember to keep track of doing that as you type stuff into the calculator. Square root of 32 and square root of 80 are a lot easier to type in than a big mess of stuff right here. There's a lot of opportunities to mess up and mistype something. All right, so we get square root of 32 and square root of 80, and that ends up as that's where we get this 5.657 is this red triangle right there. And this other one, 8.944, that's the hypotenuse of our orange triangle. Now here's the fun thing. It told us at the beginning that this is a kite. Okay? And on a kite, back in the definition, it said that we have consecutive congruent sides. So this long side right here and this long side right here are the same. That means this QR is the same as SR. All right? That side right there, the hypotenuse of the orange triangle is the same as this orange length right there. Same with the red. The hypotenuse of the red triangle right here is the same as this red length. So what we can do is we can just take these two numbers that we found and we can multiply them both times 2. And if we do that and then add those results together, that right there down at the bottom, that is the perimeter of the whole shape. All right, that is all we have for these notes. That is the end of the Topic 6 notes. All right, so y'all have a good one and take care.